stability of atom. As you all know, all matter is made up of atoms, and most of the atoms have stable structure. How do we know that atoms are stable? How do we know that atoms have stable structure? This is just inferred from what we observe. The matter that we observe has stability. Consider, for example, all the living and non-living matter in this world. We observe it to have great stability. All these figures are very well known to you, and you see them as stable structures. And that is what we infer from that matter and the component atoms are having stable structure. Now, what is the structure of atom? This concept of atomic structure was evolved in later development of modern science. Initially, atoms were considered to be just hard spheres, like billiard balls. You can see the billiard balls here, and Dalton proposed that atoms are also like billiard balls. So this was treated or considered as Dalton's model of atom, which is described as billiard ball model. Now, what were the postulates of Dalton's atomic theory, which was put forth in 1808? The first postulate is matter is made up of atoms, which are its smallest indivisible particles. Secondly, atoms of an element are all alike, but atoms of different elements are different. Atoms of each element have characteristic mass. For example, atoms of hydrogen, H, have mass 1U, while atoms of oxygen, O, have mass 16U. Another postulate made by Dalton's atomic theory is that atoms are indestructible. We cannot destroy the atoms or create the atoms. And this was perceived through number of chemical changes that matter undergoes. Here is one illustrative example of chemical change: the conversion of copper, the metallic copper, into a blue-colored salt, copper nitrate, from which the copper is regenerated on treatment with iron. We'll look at this reaction, the chemical change, also in the form of demonstration. The next postulate of Dalton's theory is that atoms combine to form molecules. For example, when any carbonaceous material undergoes combustion, the constituent carbon atoms, they combine with the oxygen atoms and form the carbon dioxide product. Similarly, the metallic sodium, if it is brought in contact with the element chlorine, then the two react with each other and form new product, sodium chloride. And the last postulate of Dalton's theory is molecule is the smallest unit of a compound. In this fashion, we come to know from Dalton's theory that matter is made up of atoms. The molecules, which are the smallest particles of compounds, they in turn are made up of atoms. So Dalton's theory gives us a view to look at the composition of matter, that matter is made up of molecules and the molecules can be described in terms of atoms using the terms either atomicity or the number of constituent elements in the molecule. So you now solve this problem based on these two concepts which evolve from Dalton's theory, that is atomicity. So complete this table and find out the number of atoms in the given molecule and the atomicity of the given molecule. And secondly, you also find out what are the constituent elements in the given molecule or compound, and how many number of constituent elements are present in the given compound. As we have seen in the first unit, that atoms are hard spheres according to Dalton's theory. Now we go on looking at the internal structure of atom. Now this concept of internal structure of atom was developed in the last decade of 19th century, and this concept was the result of many experimental findings. One important landmark in learning the internal structure of atom was Thomson's experiment. And here we have the schematic diagram of the Thomson's experiments setup. So here we are having the cathode ray tube. This cathode ray tube has a cathode, the green color shown here, which is given negative polarity. Then this is the anode, given the positive polarity. The entire tube is evacuated. There's no air inside. When the voltage is applied across the two electrodes, the cathode rays are given away by this cathode. This anode has a small hole in the center to allow the passage of the rays through it. If the rays pass through that anode, then they will reach this region, which is the fluorescent screen. So if the ray hits this screen, then there will be a flash, fluorescent flash seen. So when the cathode rays are emitted by this cathode, they travel through this anode and go ahead along this path, and the fluorescent spot is seen here, indicating that the rays have traveled all along this way. Now you can see these plates there. This is negatively charged plate and this is positively charged plate. So when these plates are operating, then it is found that the ray does not follow this straight path, but it follows a deflected path, as indicated by the flash observed at this point. Thomson learned from this experiment that the cathode rays are deflected by these electrical plates. Now the ray is attracted towards positive plate, means that the rays are made up of negatively charged particles. Another result, obviously, that all the atoms contain electrons. How this result is learned? So for that purpose, this cathode, its composition was changed. Different elements were used in the place of cathode, and it was found that irrespective of the nature of the composition of cathode, same particles were coming out as cathode rays. It means that all the atoms contain electrons. As mentioned earlier, electrons possess negative charge. And Thomson went ahead and measured the mass of the electrons, and he found that the electrons are very, very light particles. They are 1800 times lighter than the lightest element, hydrogen. On the basis of these findings, Thomson put forth his new model of atom in 1897. Now, what he had to incorporate in this model? How the negatively charged electrons are present in the atom. They also are very light particles, and there are many. So he proposed that the model of atom is like plum pudding. So in this sphere, the light negatively charged particles, the electrons, they are embedded as shown in this diagram, but the atom is not electrically charged. It has a stable neutral structure. And this stable neutral structure can be explained only by proposing that there is also balancing positive charge on the atom. So in this model, it is shown that the entire sphere is positively charged, and on this positively charged sphere, the negatively charged electrons are embedded. That is the plum pudding model proposed by Thomson. Then the next model came up with Rutherford's experiment. Now the purpose of Rutherford's experiment was to find out how these electrons are placed within the atom. In other words, what is the internal structure of atom, how the positive charge of atom is distributed, how the negatively charged electrons are accommodated in the atom, and more important, where is the mass of the atom? Is it uniformly distributed over the entire atom, or it is arranged in some regions within the atom? So for that purpose, this setup was made by Rutherford. So this is the thin gold foil. On this thin gold foil, alpha particles were bombarded. So what are alpha particles? They are the particles having mass equal to 4 units and charge equal to 2 units, the positive charge. So these alpha particles, its source was protected in this lead box, and through this hole, the alpha particles could emerge out, and the arrangement was such that they would bombard this gold foil. Then, to observe what happens to these alpha particles, this zinc sulfide screen was held there. Now the screen could be placed in different positions so that the particles emerging in any direction could be detected from the flashes. The flash that would appear at the screen, that would indicate that the particle has hit that point. So it was found that the expected fuzzy main spot appeared just in front of this, in line with the incident alpha rays. That was all right. But what was more interesting was that some flashes also appear at different positions on the screen, indicating that the alpha particles were scattered at wider angle. More interesting observation was that some alpha particles just bounced back from the foil in this fashion. Now what does this mean? This experiment was interpreted by Rutherford by saying that there is a lot of empty space within atom. That is why majority of the alpha particles simply pass through the foil. But some of the particles, they were deflected through wide angles, and some of them even bounced back. Rutherford's atomic model, which was put forth in 1911, is the nuclear model. It is the nucleus which bears the positive charge and also carries all the mass of the atom, and the light negatively charged electrons, they are outside the nucleus, and in between there is a lot of empty space. So based on this Thomson's and Rutherford's model, let us solve a few questions. So we have seen so far that the observed stability of matter is explained by assuming that matter is made up of atoms which have stable structure. To explain the stable electrical neutrality of atoms, Thomson proposed his plum pudding model. Then, to understand how the negative and positive charges and the mass of atom, they are arranged within the atom, Rutherford proposed his nuclear model. Still, it's not the end of the story, because Rutherford's model had some intrinsic drawback in it. The drawback is of the instability of atom. So see that the scientists are putting forth the models to explain the stability, but the models have some drawbacks which correspond to the instability given to the atom as per the model. So what is the source of instability in Rutherford's model? Rutherford proposed his nuclear model such that the atom is having nucleus in the core, and the negatively charged electrons, they are revolving around it like the planets around sun. But by that time, the theory of electrodynamics was well established, and according to this theory, a charged particle, if it is following a circular motion, then it loses energy. Now this, when applied to the nuclear model of Rutherford, the electron is a charged particle and it is proposed to be circulating about the central positive nucleus. But because it is a charged particle, it will lose energy. The result will be that it will now trace a spiral path with decreasing radius. Because it has lost energy, it will come closer and closer to the nucleus, and ultimately the rotating or revolving electron will fall into the central positive nucleus. So that is the fate of the revolving electron according to the established theory of electrodynamics. What does this indicate or suggest? It suggests that the Rutherford's model is not correct, because if it were the properly describing model for atom, then atom won't be stable. But reality is that the atom is stable. Right in the beginning, we have learned or we have noted that atoms have stable structure. And therefore, the Rutherford's model needs to be improved. Some additional features have to be incorporated. Now, what are the expectations from an atomic model? First, that it has to explain the stability of real atoms. And secondly, it has also to explain some other observations which are made related to atoms. What were the observations regarding the atoms made at that time? These were the emission spectra, which were found to be characteristic of different elements. Now here we have some illustrative emission spectra. At the top we have this continuous spectrum, solar spectrum, that is spectrum obtained from sunlight. So it has all the frequencies ranging from red to violet. So when these are together, we see the white sunlight. But different elements, they were found to emit some colored lights, sodium light. Now this is very familiar to us because these days we have sodium light on the street, the yellow light. The yellow sodium light, when its spectrum is taken, it contains only two frequencies. Mercury, it emits some characteristic frequencies which are shown here. Then neon emits only red frequencies, and therefore we see the neon light as red light. Now this indicates that different elements emit different light which is characteristic of those elements. And it was very natural to think that this light has the origin in the atoms of those elements. And therefore, these emission spectra of different elements also had to be explained on the basis of atomic structure. So the atomic model must have provision to explain the stability of the real atoms as well as the emission spectra that were given by different elements. To do that, Bohr proposed a new theory. He proposed some postulates, and these postulates are like this. The first postulate is that electrons revolve in discrete orbits. So they cannot take up any position outside the nucleus, but they can take only certain position around the nucleus, and that is described as discrete orbit. Secondly, electrons do not lose energy while revolving in such discrete orbits. That is very important, because the objection on Rutherford's model is that it is having the spiral path, or it proposes or it suggests that atom cannot be stable because the electrons will follow the spiral path and ultimately fall down into the nucleus. Why? Because the revolving electron would lose energy. And therefore, Bohr proposed that electrons do not lose energy when they revolve in these discrete orbits. And next proposal or next postulate is that electron gains energy on jumping from inner orbit to the outer orbit. And the last postulate is that electron loses energy on jumping from the outer orbit to the inner orbit. So this is the pictorial representation of Bohr's model. So the nucleus is positively charged. That is quite all right. There is a lot of empty space. That is also all right. But the thing is that the electrons, they occupy certain orbits. So this is one orbit. This is second orbit. Now there cannot be electron in between. The electron cannot be there in between these two orbits. So there won't be any electron here. No electron can occupy this space. So these electrons, as long as they are in this particular discrete orbit, they neither lose or gain energy as long as they are revolving in this orbit. But when the electron from this orbit jumps into this orbit, then it will lose energy. And if the electron from the inner orbit jumps into the outer orbit, it will gain energy. So energy is gained or lost by electron if it jumps from one orbit to the other. So that is Bohr's postulate. Now let us see whether you have understood the concepts of Thomson, Rutherford and Bohr's postulate, and for that purpose you solve these questions. Many models were proposed after Bohr's model, but at the beginner's level, where we are presently, knowledge of Bohr's atomic model and some additional features of atomic structure is sufficient for understanding the principles of chemistry. So, atom, what we have learned so far is that atom is made up of mainly two parts, the nucleus and the extranuclear part. The extranuclear part has lot of empty space and electrons, and the nucleus has protons and neutrons. So these atoms of various elements, they are made up of subatomic particles. So this new concept of internal structure of atom is now developed. So atom is not hard sphere, but it has some internal structure and it is made up of some subatomic particles. Now these are protons, neutrons and electrons. So proton is represented by the symbol P, neutron by N and electron by E minus. Mass of a proton is 1 U, that of neutron is also 1 U, while electron has a negligible mass compared to the other subatomic particles. The charge of proton is plus E, neutron is electrically neutral and electron has charge minus E. The proton number is characteristic of an element, and this proton number, that is the total number of protons in the nucleus of an element, it is called atomic number Z. The number of neutrons in the nucleus of an element or nuclei of an element is variable. So some nuclei may contain certain number of neutrons, while some other nuclei of the same element contain different number of neutrons. The electron number is same as proton number because the atom as a whole is electrically neutral, and therefore whatever is the positive charge in the nucleus, it has to be balanced by the total negative charge in the extranuclear electrons. The unit of mass of the subatomic particles is U, and this U, 1 U is 1.66 into 10 raised to minus 27 of kilogram. The electrical charge on proton and electron, its unit is E, it is 1.6 into 10 raised to minus 19 coulomb. What is important is that the mass number A is the sum of atomic number Z and the neutron number. So atomic number Z corresponds to number of protons, neutron numbers obviously the number of neutrons, so together is the number of nuclear particles or nucleonic particles, and each particle has mass of 1 unit, and therefore mass number is the sum of Z and neutron number. And these characters are represented in this fashion. So the symbol of element is drawn like this, and at this position the value of Z is indicated and the value of A is indicated. Now the electron orbits, the discrete orbits as proposed by Bohr. It turned out later that they are not planar orbits, but they are three-dimensional regions around the nucleus. And therefore a new term was coined, and that is electronic shells. The region around the nucleus where a particular electron is likely to be found is called electronic shell. So now we describe the atomic structure in terms of electronic shells. So electrons occupy three-dimensional shells around the nucleus rather than the planar orbits. The electrons occupy discrete shells. That is, one shell is away from the second shell, which is away from the third shell, so on and so forth. And there is some region in between where there is a concentric. So there is one shell which is nearest to the nucleus. The nearest shell corresponds to the lowest energy. So the electrons in the nearest shell or the closest shell around the nucleus, they have lowest energy. As you go to the outer electronic shells, then the electrons have higher and higher energy. These shells are numbered as n equal to 1, 2, 3, 4, etc., starting from the innermost shell. The shells are also designated by the letters K, L, M, N, which correspond to the shell numbers 1, 2, 3, 4. So using these concepts of atomic structure, let us solve a few problems. Let us now consider the electronic shells in more detail. Electrons in an atom get distributed in different shells in accordance with certain rules. So let us see what are these rules which tell us how the electrons are filled in the atom. The rule first says that there is a maximum capacity associated with any electronic shell, and this capacity is decided by the shell number. It is given by the expression 2n square. In this table you can see that for the K shell, the shell number is 1, so 2n square corresponds to 1 square. 2 into 1 square, that is 2. Then this is L, which corresponds to 2 into 2 square, that is 8. This is M shell, third shell, it is 2 into 3 square, that is 18. And for the M, that is fourth shell, it is 2 into 4 raised to 2, that is 32. The rule 2 tells us that electrons in an atom occupy shells in the increasing order of energy. So the total number of electrons that are present in an atom, they will be placed in these shells in such a way that first the lowest energy shell will be filled. When its capacity is full, then the electrons will go to the next shell, that is the outer shell. When its capacity is full, then it will go to the next higher shell. That is the meaning of this rule, that is, they occupy shells in increasing order of energy. The third rule tells us that the outermost shell of any atom can accommodate maximum 8 electrons. The capacity of the outermost shell may be more than 8, like 18 or 32, but if it is outermost shell, then it cannot accommodate more than 8 electrons. And if the K shell turns out to be the outermost shell, that means the first as well as last shell, then it cannot accommodate more than 2. So the outermost shell, which is other than K, is called octet, and if the outermost shell is K, it is called duplet. So this shell-wise distribution of electrons in the atom is called electronic configuration of the atom. So we will now apply these rules and see how the various atoms, they contain the electrons in different shells. So this is the simplest atom, hydrogen. So it has only one proton, correspondingly it has only one electron, so it is placed in the first shell. In helium, there are 2 protons and therefore 2 electrons. The capacity of the first shell is 2, and therefore both the electrons, they are placed in the second shell. The first shell. Now this is an example of a big atom, carbon. It has 6 protons, that means it has 6 electrons. So these 6 electrons, they are to be accommodated in the various shells. So first, the innermost shell, that is K shell, will be filled. Its capacity is only 2, and therefore 2 electrons will go there. The 4 remaining electrons will now go to the second shell, and therefore the configuration is 2 and 4. So numerically this configuration is indicated in this fashion, 2, 4. So 2 in the first shell, 4 in the second shell. This is oxygen, has 8 protons, that means 8 electrons. So how these 8 electrons are filled? 2 are in the first shell, the capacity is full, the remaining 6 go into the second shell, and therefore the configuration is numerically expressed as 2, 6. Then we have here example of sodium. It has 11 protons and therefore 11 electrons. So how are they accommodated in the shells? 2 in the first, then the capacity of the second shell is 8, and therefore the remaining 8 go in the second. Still 1 is remaining. It cannot be filled in the second shell, and therefore it goes in the third shell. So the configuration is 2, 8, 1. For neon, there are just 10 electrons. So 2 and 8 is the configuration of neon. Now let us see in this table how the electronic configurations of various elements are found. So in the first column we have a list of some common elements. Then this second column tells us how many protons the nuclei of these elements have. That also tells us the number of electrons, the extranuclear electrons in those atoms. Now how these electrons are filled in the various shells, or what is the shell-wise distribution of the electrons. So they are filled in these shells one after the other. For that, they have to observe what is the capacity of the corresponding shell. So for hydrogen, 1 electron, so it is occupying the K shell, the configuration is 1. Then helium, 2 electrons, the capacity is full, the electronic configuration 2. Carbon, 6 electrons, so 2 in K, 4 in L, so 2, 4. Nitrogen, 7 electrons, 2, 5. Fluorine, 9 electrons, so the shell-wise distribution, that is the configuration is 2, 7, in this fashion. If you go ahead to bigger elements, sulfur, the atomic number 16, meaning there are 16 electrons. So how they are distributed in the shells? 2 in the first shell, 8 in the second shell, and the remaining 6 in the third shell. So 2, 8, 6. If you go to bromine, there are 35 electrons in the atom of bromine. So how are they distributed? First, the innermost shell is filled, then the second shell is filled to its maximum capacity, then the third shell is filled to its maximum capacity, and the remaining 7 electrons are placed in the last shell. So the configuration is 2, 8, 18, 7. The configuration of krypton, having 36 electrons, is 2, 8, 18, 8. So let us now solve this activity based on the electronic configuration of atoms that we have learnt just now. Now we proceed ahead with another concept which is related to the term valency. We have seen that atoms are stable, and to explain their stability, scientists have come up with different theories. But what is stability of atom? If the atoms are so stable, then why do they react and form compounds? Why do elements react and form compounds? So to understand this reactivity of elements to combine with each other and form compounds, we go ahead to look at this new dimension of stability of atom. So what is this valency? To understand valency, we have to understand some properties of elements, and these are that atoms of majority of elements have tendency to combine with other atoms. The atoms may combine with other atoms which are similar or different. The valency decides the molecular formula of molecule which is formed by combination of atoms. Valency is the measure of combining power of atom and is expressed as a number. Generally, elements have same valency in different compounds. Let us go through the next table, which will tell us about all these features of valency. So consider here the molecular formulae of some simple compounds or elements. So H2 is the molecular formula of hydrogen. 2 hydrogen atoms are combined to each other to form the H2 molecule. From this we infer that valency of each hydrogen is combination of H and Cl. We already know that valency of hydrogen is 1, and 1 hydrogen combines with 1 chlorine, means valency of chlorine is also 1. H2O has combination of H and O. We already know that hydrogen has valency 1, and it follows that oxygen has valency 2 because oxygen is combining with 2 hydrogen atoms. In sodium chloride, chlorine with valency 1 is combining with only 1 sodium atom to form NaCl, and therefore valency of sodium is also 1. In chlorine gas, elemental chlorine, 2 chlorine atoms are combining with each other because the valency of chlorine is 1. In ammonia, NH3, there are hydrogen atoms and nitrogen combining with each other. We have already seen that hydrogen has valency 1, so it follows that nitrogen, which is bonded to 3 hydrogens, has valency 3. In the same manner, it can be inferred that carbon has valency 4, magnesium has valency 2, and helium and neon, these have valency 0. How we know that? Because they exist in atomic state. They don't form any molecule, and therefore we infer that helium has valency 0, neon has valency 0. So what are the characteristics of valency? The valency, it will turn out, that is related to the electronic configuration, and we'll shortly look at that. The electrons in the outermost shell are involved in combination with other atoms. And combination of different atoms with each other is nothing but chemical reaction. In the chemical reaction, only the outermost electrons are involved, and therefore these outermost shell electrons are called valence shell electrons or valence electrons. The valency of an element is 0 when the valence shell is complete. So we already learnt earlier that argon or neon or helium, they have complete octet or duplet, and their valency is 0. So when the valence shell is complete, the element has 0 valency. The valency of an element is same as the number of valence electrons when the number is 4 or less. On the other hand, if the number of valence electrons is 4 or more, the valency of the element is given by the number by which the valence shell is short of completion. All these points will be clear when we look at the electronic configurations of the various elements and their valencies. So, this is hydrogen. It has the electronic configuration 1. The duplet is short of 1 electron, and therefore the valency is 1, as seen from the molecular formula H2. That is 2 hydrogen atoms joined to each other. So 1 hydrogen combined with only 1 more hydrogen, so valency is 1, which corresponds to the number 1 of the valence electrons. How this is valence electron? Because this is the only shell, the first shell, that is K shell, present in hydrogen, and when it is the outermost shell, it is called valence shell. So the first and the outermost shells in hydrogen are the same. That is K shell, the capacity 2, and it is short of 1 electron. Helium, the duplet is complete, so it doesn't form any molecule, valency is 0. Carbon, the valence shell has 4 electrons. It corresponds to the valency 4 as seen from the molecular formula CH4. Nitrogen, the configuration 2,5, the valence shell contains 5, which is short of 3 electrons for the complete octet, and therefore the valence is 3, seen from the molecular formula NH3. Oxygen, the configuration 2,6, the valence shell contains 2 electrons short of complete octet, and therefore valence is 2, as seen from the formula H2O. So oxygen forms or combines with 2 hydrogens. Fluorine, the configuration 2,7, the valence shell is short of 1 electron for complete octet, and therefore the valence is 1, as seen from the molecular formula HF, fluorine combining with only 1 hydrogen. Neon, the valence shell is complete, so no molecule form, and indicating valency 0. Some more examples are here. Consider aluminum. It has 13 electrons, configuration 2,8,3. So it contains 3 valence electrons, so valence is 3, as seen from the molecular formula AlCl3. Chlorine. The 17 electrons are distributed 2,8,7. The valence shell short of 1 electron for complete octet, so valence is 1, as seen from the formula HCl, chlorine combining with only 1 hydrogen. Same thing with bromine, 2,8,18,7, valence shell short of 1 electron for complete octet, and therefore valence is 1, as seen from the formula HBr, Br combining with only 1 H. Argon 18 and krypton 36 both have complete octets, and therefore the valence is 0, as is learned from their inability to form any molecule. So what we conclude is that the atoms of elements with complete duplet or complete octet do not combine with other atoms to form molecules. This indicates that there is spatial stability associated with complete octet or duplet. So this gives us a new idea of, or a new dimension of the stability of atom. We have started with stability of atom, and therefore Dalton proposed that it is indestructible. Then stability was related to the electrical neutrality. Then the stability is related to occupying discrete orbits in the Bohr's model. And now we describe the stability of atom in terms of the electronic configuration having complete octet or complete duplet. So atoms which have incomplete octet or incomplete duplet are unstable, and these are the atoms which have tendency to combine with other atoms. Thus, stability of atoms is related to electronic configuration. Based on this, you can complete these tables